In this deck, we focus on a gate operations challenge that sits at the center of container terminal performance. How to allocate appointment time slots to trucks in a way that reduces congestion, lowers truck waiting time, and keeps terminal resources used steadily instead of in harmful peaks. The core idea behind a static truck appointment system is pre-allocation. Rather than letting trucks arrive purely first come, first served, the terminal assigns time slots ahead of time using known demand patterns and capacity limits. The goal is to turn unpredictable arrival waves into a controllable flow that operators and trucking companies can plan around. Consider a busy setting like the Port of Los Angeles, where over 15,000 truck transactions can occur each day across multiple terminals. The major issue is that arrivals come in waves. Peak hour spikes often create long queues, while off-peak hours leave gates and staff underutilized. In the scenario, peak periods are typically 8 to 10 a.m. and 2 to 4 p.m., and truck waiting times can reach 2 to 3 hours during those peaks. That has direct cost and service implications: higher operational expense, frustrated drivers, more local air pollution from idling, and damaged community relations. This slide grounds the problem in concrete capacity. The terminal operates 16 hours per day from 6 a.m. to 10 p.m. It has 8 processing gates, and each gate can handle an average of 4 trucks per hour. The gate is not handling a single uniform job type. The facility must accommodate container pickup, container delivery, chassis exchange, and documentation processing. Because these transaction types differ in processing time and resource needs, the appointment system has to manage not only volume, but also mix. We solve the static appointment problem through a tiered toolkit. Tier 1 gives a mixed integer programming formulation that defines an optimal baseline under capacity and consistency constraints. Tier 2 introduces a fast earliest deadline, first heuristic for daily operational use. Tier 3 upgrades search quality through ANET colony optimization. Tier 4 uses supervised learning with a random forest model to predict assignment quality. Tier 5 embeds decisions inside an integrated digital twin to support monitoring, what-if analysis, and proactive rescheduling. Tier 1 treats the appointment plan as an optimization problem. Assign each request to a time slot while respecting slot capacity and ensuring the implied gate workload is consistent. This formal model is valuable because it makes feasibility explicit and gives you a standard for what optimal looks like under the stated rules. A key modeling element is deviation. If a truck prefers a certain time slot, shifting it earlier or later is allowed, but it carries a penalty. The objective then trades off 2 things: the total weighted deviation from preferred times and imbalance in gate utilization that would create operational peaks. This slide defines the main sets that structure the model. You have a set of time slots, a set of appointment requests, a set of gates, and a set of service types. Operationally, sets are the vocabulary of the model. They ensure that every decision is tied to something real. A specific request is assigned to a specific time slot, and the workload implied by all assigned requests is reflected in gate-level counts. Parameters describe what is given before optimization starts. Each request has a preferred time slot and a priority wait. Each time slot has a capacity, meaning the maximum number of trucks that should be scheduled into that slot. You also have penalty settings that define how strongly the system tries to keep trucks close to their preferred times versus how strongly it tries to smooth gate utilization. These parameters let the terminal tune the appointment policy to match service promises and staffing reality. Decision variables represent the choices the optimizer makes. The primary decision is whether request R is assigned to time slot T. Additional variables track gate workloads per time slot and deviation values that measure how far an assigned slot is from a request's preferred slot. The practical meaning is straightforward. Each assignment decision is a commitment the terminal makes to a trucker. Deviation variables quantify how much the terminal is asking the trucker to shift, and gate workload variables quantify how much pressure the schedule will create on specific gates. The objective combines 2 operational goals. First, it penalizes deviation from preferred times, scaled by request priority. Higher priority requests pay a larger penalty when shifted. Second, it penalizes gate utilization imbalance within each time slot. Even if total volume is feasible, a schedule that concentrates work unevenly across gates can create micro bottlenecks, longer service times, and unstable queue dynamics. The objective pushes the plan towards smoother, more predictable operations. This constraint enforces completeness and clarity. Every appointment request must be assigned exactly once. Operationally, it prevents two failure modes. The model cannot solve congestion by silently dropping hard requests, and it cannot assign the same request to multiple slots in a way that would look good numerically but be impossible in real execution. This constraint limits the number of trucks assigned to each time slot, so the schedule respects the planned gate capacity. This is where the appointment system actually reduces congestion. If capacity is enforced, peaks get clipped and some demand is shifted into off-peak capacity, where gates and staff would otherwise be idle. This constraint ensures internal consistency between total appointments scheduled in a time slot and the workload allocated across gates in that slot. Operationally, it forces the plan to be executable. It is not enough to say, this slot has 5 trucks. You must also ensure that gate-level staffing and gate-level assignments can support that volume without violating the implied processing limits. This constraint defines how deviation is calculated. Deviation is the difference between a request's assigned slot and its preferred slot. In plain terms, it turns how unhappy is the request with this assignment into a measurable quantity that can be weighted by priority and minimized in the objective. This constraint enforces that deviation quantities are non-negative. A deviation is a magnitude, not a sign direction. Operationally, non-negativity prevents the optimization from canceling shifts in opposite directions in a way that would hide real service impacts. This constraint states that assignment decisions are yes or no. A request is either scheduled in a slot, or it is not. This matters because appointment assignment is a discrete commitment. Fractional assignment would have no operational meaning and would produce a plan that cannot be communicated or executed. This constraint enforces that gate workload values behave like counts. They must be non-negative and integer. Operationally, a gate cannot process 2.3 trucks. Gate counts are discrete workloads used for staffing, lane management, and throughput planning. This slide visualizes the static appointment allocation matrix. You can interpret it as a time-by-request view of who is scheduled when. The value of the matrix is auditability. It makes it easy to see whether certain time slots are overloaded, whether capacity constraints are respected, and whether the schedule is aligned with preferred arrival patterns. This example uses 6 requests and 4 time slots, with capacities 2, 2, 1, and 1. The preferred times are 1, 1, 2, 2, 3, and 4, with weights 1, 1, 2, 1, 1, and 2. The optimal assignment matches all preferred times while respecting capacity, producing a total deviation penalty of 0. This is an important teaching example. If capacity and preferences align well, the system can deliver both low congestion and high satisfaction at the same time. Tier 2 uses a practical greedy rule: earliest deadline first. Requests are sorted by preferred time and priority, then assigned to the earliest feasible time slot. Operationally, this heuristic is attractive because it is fast, transparent, and easy to deploy. It tries to place each request at its preferred slot first, then searches forward for capacity, and if needed, considers earlier slots. The result is a workable daily schedule without heavy computation. This slide shows a timeline structure for appointment scheduling, emphasizing flow across the operating day. Use the timeline to build intuition. The appointment system is not only a list of assignments, it is a demand-shaping tool. It spreads arrivals over time so the gate can work steadily rather than oscillating between overload and idleness. In the first code section, you typically see data structures for requests, preferred slots, weights, and remaining capacity per slot. Operationally, the critical detail is that capacity must be updated after each assignment. The heuristic is only correct if every placement decision reduces available capacity and prevents future assignments from exceeding limits. This section usually contains the greedy assignment loop. Requests are processed in priority order, and the algorithm searches for the first feasible slot. The practical strength here is speed. Even when the request list is large, sorting and simple scanning can produce schedules fast enough for daily planning cycles. This section typically covers reporting and validation, showing which slot each request was assigned to and computing the total deviation penalty. Operationally, reporting matters as much as assignment. Terminal teams need outputs they can audit, and trucking companies need clear appointment confirmations. The reported output shows the heuristic assigning all 6 requests to their preferred slots, with total deviation penalty 0. It also shows a gate utilization matrix that is balanced across gates. The lesson is that simple rules can be optimal for small structured instances, and that a static appointment plan can achieve both feasibility and fairness when demand is not fundamentally over capacity. Tier 3 uses ant colony optimization to search for stronger schedules, especially when the instance is larger or more conflicted than what a greedy heuristic can handle. Each artificial ant constructs an assignment probabilistically while respecting slot capacities. Pheromones represent learned preferences for certain request-to-slot pairings, and the colony converges toward low-penalty schedules while still maintaining some exploration. This slide focuses on how an ant chooses a slot for a request. The choice blends pheromone strength, representing learned experience, with a heuristic preference for assignments close to the preferred time. Operationally, this balances 2 behaviors. The method exploits patterns that repeatedly lead to low penalty, but it continues to explore alternatives, which helps avoid getting trapped in poor local assignment patterns. This visualization shows the ant colony optimization solution construction process. Think of it as repeated experimentation with memory. Ants propose full schedules, the best schedules reinforce pheromones, and evaporation prevents the colony from locking in too early on a suboptimal idea. In the first code section, you typically see initialization of pheromones, definition of feasibility checks, and the representation of capacities and requests. Operationally, feasibility checks are non-negotiable. The algorithm should not reinforce assignments that violate slot capacity, because that would teach the colony the wrong behavior. This section usually contains the route, assignment, construction loop for each ant. For each request, select a slot based on transition probabilities and remaining capacity. The key practical idea is that probabilities change as capacity is consumed. As slots fill up, those slots should become infeasible, pushing ants to discover workable alternatives. This part often defines the cost or penalty of a complete assignment. Penalty increases as weighted deviation grows and as imbalance patterns emerge. Operationally, cost definition is what makes ant colony optimization target the right outcome. If cost aligns with terminal goals, pheromone reinforcement will concentrate on schedules that reduce congestion and preserve service. This section typically shows pheromone evaporation and deposition. Evaporation reduces all pheromones slightly, and deposition increases pheromones along assignments used in strong solutions. Operationally, evaporation prevents premature convergence. Deposition is the learning signal that turns repeated success into higher probability of reselection. This section usually contains the main iteration loop. Run many ants, evaluate results, update pheromones, and track best and average penalties across iterations. In practice, this logging is essential for trust. Operators and analysts want to see whether the algorithm is actually converging and whether improvements are consistent. This slide reports a convergence snapshot. At iteration 0, the best penalty is 4.0 and the average is 8.45. At iteration 20, the best is 2.0 and the average is 4.2. At iteration 40, the best is 1.0 and the average is 2.85. The final best penalty is 1.0 with a feasible assignment across 8 requests. The operational takeaway is that the colony improves through iterations and can discover near best schedules that a simple greedy rule may miss when the instance becomes more crowded or conflicting. Tier 4 uses supervised learning to predict assignment quality from historical data and engineered features. Instead of searching directly each time, the model learns patterns that link conditions like utilization, preferred time, and weather to assignment outcomes. Operationally, predicted quality scores can help recommend time slots for new requests, especially when demand patterns repeat. This is a decision support tool. It can propose strong candidates quickly, and then the terminal can apply rule checks and capacity constraints. This slide defines the feature vector used to describe a request and the system context. It includes items such as preferred time, request weight, cargo type, carrier identifier, current utilization, day of week, hour of day, seasonal index, and weather factor. The practical meaning is that model performance depends on what the model can see. If utilization and timing features are missing, the model cannot anticipate congestion. If cargo and carrier features are missing, it may miss systematic differences in processing needs. This slide defines the target quality that the model learns to predict. Quality is higher when weighted deviation penalties are lower. Operationally, this ties machine learning directly to the business objective. If the target is aligned with what the terminal values, the slot recommendations will be meaningful rather than just statistically convenient. This slide shows the machine learning enhancement architecture. Think of it in two phases. Offline, you train on historical appointment and performance data. Online, you generate a ranked list of recommended slots for each new request. The terminal can then choose from those recommendations, subject to capacity and operational rules. In the first implementation section, you typically see dataset preparation, feature extraction, handling categorical variables, and splitting into training and validation sets. Operationally, data quality is central. If historical data has missing utilization measurements or inconsistent timestamps, the model can learn wrong correlations and produce misleading recommendations. This section usually contains training and evaluation of the random forest model, plus generation of predictions for candidate time slots. A practical benefit of random forests is robustness. They can capture nonlinear relationships and interactions without requiring heavy tuning, which makes them useful as a first deployable model in operational settings. This slide reports model metrics. Training R-squared is 0.8724, and validation R-squared is 0.8456. It also reports top feature importances. Current utilization at about 0.2845, preferred time at about 0.2134, and request weight at about 0.1876. The takeaway is that system load and timing dominate appointment quality, which matches operational intuition. This slide shows ranked recommendations by predicted quality score. Time slot 2 has quality 0.7845, and time slot 3 has quality 0.7234. The key message is how the model is used. Not as a single hard decision, but as a ranking. The terminal can apply capacity checks and business rules and then select the best feasible slot from the ranked list. Tier 5 introduces an integrated digital twin that simulates gate, yard, equipment, and traffic subsystems in a synchronized environment. Operationally, the twin supports what-if analysis and proactive rescheduling before congestion becomes severe. It also manages multiple time horizons, from second-level monitoring to week-level planning, which enables both real-time control and strategic improvement. This slide visualizes the integrated digital twin system architecture. Use it to understand the data loop. Sensing and operational systems feed the twin runs prediction and optimization, and recommendations flow back to operations. The architecture is designed to make appointment decisions grounded in the full system, not just the gate in isolation. This code section typically defines core data structures for representing the current terminal state, such as scheduled appointments, gate status, and key performance indicators. Operationally, a clean state definition is the foundation of the twin. If the state is incomplete, the twin cannot correctly simulate downstream effects like yard congestion or equipment shortages. This section often implements data ingestion and synchronization from sensors and operational databases. In practice, synchronization latency and reliability determine whether the twin is trustworthy. If the twin is updated too slowly or inconsistently, it can recommend actions that are already obsolete. This section commonly contains simulation logic that predicts gate processing, queue buildup, and resource utilization. Operationally, simulation is what allows proactive action. Instead of reacting when trucks are already waiting, the terminal can anticipate a queue forming and shift appointments earlier or later while there is still flexibility. This part usually integrates predictive models such as short-term congestion forecasts or demand forecasts and connects those forecasts to appointment adjustments. The key point is that forecasts must be actionable. A prediction is only valuable if it drives a scheduling change that reduces waiting time or prevents a capacity violation. This final code part typically implements an optimization or rescheduling workflow inside the twin and generates recommended changes and dashboards. Operationally, this turns the twin from a visualization tool into a control tool. It can propose concrete moves like shifting specific appointments, reassigning resources, and communicating updated plans to stakeholders. This slide presents a concrete integration scenario. At 9 a.m., 15 new appointment requests arrive while utilization is at 85%. A Gate 3 sensor malfunction reduces capacity by 25%, and weather prediction shows a 40% chance of rain in 2 hours. The twin responds by redistributing 6 appointments and achieves a 23% reduction in predicted waiting times while maintaining 96% customer satisfaction. The operational lesson is that proactive, system-aware rescheduling can protect service even when disruptions occur. This practice question asks you to formulate a mixed integer model for a terminal with 3 gates, 6 time slots, and 8 requests. Each gate can process 2 trucks per time slot, and you must compute the total deviation penalty. Treat this as a completeness exercise. Define assignments clearly, enforce slot capacity, and ensure every request is assigned once. The goal is to confirm that you can write a full baseline model that matches the Tier 1 structure.